We're now going to look at some examples of matrix vector multiplication. By the way, we'll see it throughout the rest of the course, so these are just, think of these as just your first examples that you're seeing. However, they should already kind of be clear that it's going to do something that is going to be useful for us. Okay, so we start with some really dumb stuff, you know, the basics, okay? So if I multiply a zero matrix by any vector, I get zero, right? And so, I mean, you look at the equation 0x equals 0 and your eyeball says, yeah, sure, what else was it going to be? But it's important to understand that we're actually loading into these 4 characters. That's quite a strong statement, right? 0 is a matrix, x is a vector, and 0 here is a vector, okay? Here's one, that identity matrix. I don't know if you remember the identity matrix. It's a matrix with 1s on the diagonal, like this, and 0s everywhere off the diagonal, right? So something like that. There you go. There's a 4x4 identity matrix. If you multiply that by any vector, you get the vector back. And that's, by the way, why it's called an identity matrix, right? It does absolutely nothing if you multiply it by a vector. In other words, it gives you the same vector back. And you should check that. I mean, let's just multiply this by, you know, x1, x2, x3, and x4. And let's just audit this. Let's do the third, let's fill in what the third entry in this case, ix is. Well, that says, please walk across that column, right? That row, I'm sorry, and go down here. And you basically multiply 0 by x1, 0 by x2, 1 by x3, 0 by x3. You multiply that, you're going to get x3. So you get x3 here, okay? And, you know, sure enough, x3 is the third entry of this, and it's the third entry of that. And, okay, I mean, that was silly. But the point is you should do this to just check, you know. Okay, all right. Now, the inner product. From basically part 1 of the course on vectors. We wrote it as A transpose B. As I said last time, I misspoke on a number of occasions and accidentally referred to it as A transpose B. That was bad because, in fact, I had not defined what a transpose was or anything like that. So most of the time, I think I got it right and referred to A transpose B as the inner product. Henceforth, though, I'm fully allowed to refer to A transpose B either as the inner product of A and B, the 2 vectors, or literally A transpose B, which means transpose A, which makes it a row vector, and multiply it, matrix vector multiplication by B. Okay, so that's it. And it's nice. It means that it explains that notation fully. It's nothing new, it's nothing special. Okay, and so it's really cool. It says take an n vector, form, when you transpose it, it becomes a n row vector, and then you multiply by the n vector b. And the result, by the way, is a 1x1 matrix, which we just consider to be a number. Okay. So our notation is completely consistent with transpose and vector, matrix vector multiplication are completely consistent, and in fact are exactly our notation for the inner product. Okay. Let's look at some other ones. Here's an example. You recall what it means to demean a vector. To demean a vector says take x, take the average of all of its entries, and subtract that number from every single entry in A. Okay, and what that means, of course, is the new vector is kind of the same as the old one, except now except the mean of all the entries are 0, or something like that. Okay, the mean of all right. So that is accomplished with x tilde equals ax, where this is the matrix. And we can even sort of see that that's right. So let's look at x1 down to xn here and multiply this. Well, and let's say that we believe that that's x tilde 1. And let me see what it is. Let's just check that first entry. X tilde 1 is going to be this number times x1 plus this number times x2 all the way up to that. And that's going to be this. X tilde 1 is equal to, now the 1 minus 1 over n, if you don't mind, I'm going to write it this way. I'm going to write it as x1 minus 1 over n x1. It's weird, but that's what I'm going to do. Minus 1 over n x2. And then this goes on for a while. And then I have minus 1 over n times xn. Hey, look at that. This is the negative of the average. So in fact, this is right. You can check. So this is a fancy way, I mean, it's a silly way to demean a vector, but you can think of it as just a matrix vector multiplication with this matrix A. Yeah. By the way, in these connections, when we see what multiplying by a matrix to a vector does, um, and we interpret it some way, like this is demeaning, you're going to want to develop the skill of going both ways. Like I show you a matrix, and then you tell me what it is in words. I mean, if it's just some weird random matrix, the answer is I don't know. But the point is, I should have been able to give you that matrix and say, what does it do? And then you would come back and say, oh, it simply subtracts the mean of the entries from every entry of X. It's a demean. People would even refer to that as the demeaning matrix. So anyway, and you'll want to go back and forth. So we'll get to that later. Okay, here's a matrix which illustrates what I was just talking about perfectly. It's n minus 1 by n difference matrix. Here's D. It's very sparse, right? By the way, most of the entries are 0. A few entries are minus 1 and some are plus 1. So here's what it looks like. It says minus 1, 1. Then the next entry is then all zeros, 0, minus 1, 1. And what happens is we simply put a vector here, multiply this out, and see what we think, what happens, okay? So when I multiply this row by this, if I do this row by this vector here, what I'm going to get is minus x1, that's from this entry, plus x2, and then everything else is 0. So what you're going to get is this. dx is x2 minus x1, then x3 minus x2 because of this here, and so on. And you get n minus 1 of these, and you can see what this matrix does. It takes the first difference, the difference if x is a vector, it simply takes the difference of consecutive entries, right? So now, by the way, a lot of times, if these were just x's that are, if the different entries of x are features and they have no relation to one another, this has no meaning and no use. But for example, if x is a time series, this is super interesting, right? So if x is the rainfall over at a different day on different days, then dx tells you the change in rainfall from a given day, well, from tomorrow, from today, or something. The daily change in rainfall is what it does. If it is positive, it means there was more rain on that day than yesterday. If it's negative, it means there was less. Okay, so you could even, if you like, you could even start thinking in the back of your mind that this is something like a derivative, right, or something. I mean, don't take that too seriously, but it's something like that. Okay, so that's a matrix. You will see this many, 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 many times, and you might as well just get used to it right now. It's a difference matrix, and we should have been able to do this with you for both ways, right? That I should have showed you that matrix and said, what does it do? And eventually you could have said, it takes the consecutive differences, right? So here's something that comes from that. It's a beautiful thing. It's the norm squared of dx, and that's called the Dirichlet energy. Dirichlet was a mathematician, and it's a measure of the wiggliness for x if x is a time series, because you know what this thing is? This is exactly equal to the sum of xi minus xi minus 1 squared. And the sum goes from I equals 2 to n. That's what it is. So it's literally the sum of the squares of the consecutive differences. So you could have dx, the Dirichlet energy is 0 for any vector which is, quote, constant, meaning all the entries are the same. Then the Dirichlet energy is 0. If x is like crazy wiggly, or first it's plus 10, minus 10, plus 10, if it's alternating sign, the Dirichlet energy is going to be very high, right? So that's the idea behind that. That's going to come up later in the class, exactly this kind of thing. Okay. Here's another example. This one is from finance. So let's let R be a T by N matrix of asset returns, right? And so the rows represent time periods, consecutive time periods, or let's say days, the trading days, right? And the columns represent a particular asset, and we have a universe of N assets. That is the slang that you would refer to the set of assets you're looking at, let's say at a quantitative hedge fund. You'd say, what what's your universe? And in this case, n is the size of the universe of assets. Okay. And so Rij is the return of asset I, it's the return of asset J in period I. Okay. Let's look at an n vector W, and it gives a portfolio. And it gives you, let's say, the investments in the assets. They could add up to 1, in which case it tells you the proportional investments. Like, I put 10% of my portfolio is in asset 1, 20% in asset 2. It could even have negative numbers, which represents short positions. Negative ownership. I think we talked about that before. It's weird, but it's possible. And then RW, literally by sticking the matrix times the weights, what you will get is a vector of the time series of your portfolio return. Okay, so it's really cool, right? So we could just do a quick example, right? So I'm not going to work everything out because it's kind of goofy. I'll do let's see. Okay, this is 0.02 minus 0.01. I'm just going to do a couple here. 0.03 and minus 0.04, and I don't know what this is. This is going to be 0.01 and 0.01. Okay, so it's silly because it's so small. But the point is 3 time periods, so 3 trading days, 2 assets. I don't know what they are, Google and Intel, or I couldn't care less, right? Okay, so here are the 2. And then, let's ask ourselves, like, what does it mean? Well, the first column gives you the time series of returns of the first asset. The second column gives you time series of returns of the second asset. So for example, the second asset lost 1%, gained 1%, then gained another percent. Okay? The first asset gained 2%, then 3, then minus 4%. Okay? Now I'm going to make a portfolio of these, and I'm going to make it super simple because I don't even want to mess with it. Okay? Here's my portfolio. It's going to be 0.5 and 0.5. So I'm simply going to invest equally in these 2 assets. Okay, and that's what the 0.5 means. Okay, so it's the proportions that I invest in it. And so let's see what happens when I get RW. When I multiply RW, actually, interestingly, what I'm getting is a 3 vector, and it's this row times that. And I'm actually, if you multiply by 0.5, you're actually taking the average, right? So the average of up 2% and down 1% is, let's see, it is down, it's plus 0.005. I hope I did that right. Okay, and the average of the other 2 is going to be 0.02. I'll put the O there. And the average of these is minus 0.04 and plus 0.0 is minus 0.03 divided by 2 is maybe minus 0.015. There we go. I made those up in real time. I hope they're right. If they're not, sorry. But in any case, see, that's the nice part. If I had a class in front of me, somebody could wave their hand and say that's wrong. And I would say, good, thanks, just checking on you. But I can't do that now. So, all right. So let's see what it means. It means that if I invested equally in these 2, here would have been the sequence of my portfolio returns, right? So, on the first period, I'd say, oh, good news, your first asset went up 2%. And you'd say, bad news, your second asset went down 1%. But my portfolio went up 0.5%, right? On the second one, it'd be, hey, great news, your first asset went up 3%, your second went up 1%. I'm 50-50, so my portfolio goes up 2%. Okay, so that's kind of the idea. Okay, so that's it. And now it's really cool. So when you do matrix vector multiplication, when W is a portfolio and R is this asset returns, many assets, many time periods, what you get is you get the time series of the portfolio return. So for example, if I take the average of RW, that's literally the portfolio mean return, because this is like a return time series. And if I take the standard deviation, that's the risk, right? So just a handful of things now we're able to very quickly describe real things, right? So if I have a return matrix, and so this way, for example, we could discuss different weight vectors. Somebody could say, well, here's my weight vector. Someone says, where'd it come from? And they could say, it's none of your business. Someone else would say, here's my weight vector. And you'd say, cool. we can then calculate for both of them, for both those weight vectors, what would be the return time series of their portfolios. And then we can actually evaluate each one on a mean, which is the mean return, and on the standard deviation of that time series, and that's going to be the risk. And maybe they're incomparable, but maybe one is better, maybe one dominates the other. Dominates meaning that it has higher return and lower risk. But so this is the idea. But and look how quick it's just a handful of concepts we have, and we're just shoving them together. Here's one, a feature matrix and a weight vector. So here, what I do is I form a feature matrix. So the columns of a feature matrix are the features for the different items. In this case, I have capital N items, and each one is an n vector. I have n features, and so I shove them together in a matrix, which I'm going to call the feature matrix. And so the columns are going to be, well, the feature vectors for the items. Okay, here if I make W a weight vector, and if I form X transpose W, let's be super careful here. X has size n by n. X transpose has size n by n. Okay, and then we propose to multiply that by an n vector, and that's cool. So yeah, I should mention something here. You're going to want to turn on a syntax checker. Well, the same way any kind of computer language has one, but you need to be one yourself. It's a mathematical syntax checker. And you just want to make sure everything is cool, right? So, I mean, somebody might mess up and write here XW, but you should immediately, that should throw an alarm, because you should say, excuse me, hello, whoa, slow down here. You cannot multiply, a little n by capital N matrix by a little n vector, unless they're equal, right? So that's what you just want to be checking, that the syntax rule, that the rules are correct, right? So, okay, any more than if I walked up down the street and said that a 2 vector and a 3 vector are equal, right? It doesn't conform to syntax, so you want to check. Okay, so what you get in this case is, if I form this, then this is basically the same as taking the inner product of each one of our feature vectors with this weight vector. And we had interpreted that before as scores, right? So for example, each of these, the items could be individual people. The xi is for the ith person. It is a feature, it's a set of features that characterizes that person. And it should be things like the total amount of late payments on his credit card in the last 6 months. I'm just making this up, okay? Another one could be the fraction of times they pay off their whatever feature. One could be, have they actually declared bankruptcy in the last 5 years, right? Something like that. So I have all sorts of features, right, related to them. Okay, that's a feature vector. And then W is some weight vector, which I don't know what it is. And then this score could be could develop a credit score, right? So it says here's the credit score. And in which case, by the way, everything here is completely interpretable, right? So W1, for example, tells you how much does feature 1 figure in to your credit score. And so, for example, if the first feature is either 0 or 1, 0 if that person has not declared bankruptcy in the last 5 years, 1 if he or she has, then we would expect W1 to be negative, meaning that if a person has declared bankruptcy in the last, 5 years, we would expect their credit score to be lower than if they had not. So it's all perfectly interpretable. But once again, matrix vector multiplication with a transpose in here gets you gets you something that's very interesting, and potentially already should be clear that this is we're bordering on, if we're not already there, useful. Another beautiful interpretation of matrix vector multiplication is just input-output. So there we simply write like y equals ax. These are almost the traditional symbols too. You think of, and what you do is you think of x as an input or an action, and you think of y as an output or outcome or result. Okay, and tons of examples of this. We'll see a bunch of them, but that's kind of the idea. And then you think of like matrix vector multiplication as simply an action. What it does, it's what it maps the action to the result. Okay, so and in which case we can have this very simple generic interpretation. So for example, aij, that's the ij entry. That's the factor by which yi depends on xj. Okay, if it's 0, it means it doesn't depend on it. If it's large and positive, it says that when xj goes up, yi goes up. If it's large and negative, it says that when xj goes up, yi goes way down, right? So that's kind of the interpretation. Oh, here's an interesting one. If the matrix A is lower triangular, right, then it says that yi only depends on x1 up to xi, okay? And by the way, if these are time series, it's kind of awesome because that means that that's like causality. It says that, you know, the ith outcome, and we think of I as a time period, it really can only depend on what x was doing in time period I, which is now, I minus 1, that's like, let's say it's daily, that's yesterday, I minus 2, that's day before yesterday, and so on, right? So their lower triangularity corresponds to, well, you know, causality, basically. So this is the idea. So this is another interpretation. We're going to come to this many, many, many times. Finally, we're going to talk about the complexity of some of these matrix operations, meaning how many flops does it take? And again, we're going to approximate it grossly because that's what people do, just to get a rough idea. So, okay, so first of all, an m by n matrix A is stored on a computer as an m by n array of numbers. So, you know, I mean, although an array would be understandable to a mathematician, that's actually the language of computer science and computer languages. Okay, I mean, it's fine, but you just have to keep two dialects, I guess, to describe the same thing, and just make sure you know which dialect you're speaking. Okay. Now, for a sparse matrix, it's stored in a different way. That you store, roughly speaking, all you do is you store the non-zero values, and so you would give a list with I, j, and value. Okay, so like a dictionary, if you're familiar with that in some language you're working on, or there's other exotic ways that people describe sparse matrices. Doesn't matter. Okay, now first let's talk about the simple ones, right? If I add two matrices, well, that's silly. I just add up mn numbers. So that's mn flops. If I do scalar matrix multiplication, it's the same. I multiply that same scalar by every entry of the matrix, and that's mn flops. How about matrix? Oh, I should ask you this. How many flops is in the transpose, forming A transpose? Well, I guess the conventional answer to that is 0, because you don't do any multiplications, adds, or anything. You're literally just moving entries from one place to another. Now, the fact is, it actually doesn't cost 0 time to transpose a matrix, right? Because, you know, memory, you have to access memory and then move it somewhere else and all that sort of stuff. So this just shows you one of the shortcomings of a flop count. It's still, however, quite useful, the idea of a flop count. So summary on that weird discussion is this. The complexity of forming a transpose is, well, 0. It involves 0 floating point operations. No adds, no subtractions, no multiplies, no divisions, no square roots. Okay. Let's look at matrix vector multiplication. Well, let's figure that out. Well, we could do it this way. We could think of it this way. It's actually calculating for each row or each entry of the product, that's of which there's m, we calculate an inner product with a row of A and X, okay? And that, as you recall from last time, takes 2n minus 1 flops, right? It takes n multiplications and then n minus 1 additions. And so 2n minus 1. And the minus 1 we just get rid of, and we simply say that it's 2mn flops. That's it. Now, by the way, if A is sparse, you only have to multiply the terms that involve non-zeros. I mean, of course, right? But this is it. It's 2mn flops, right? So just for fun, let's figure out, let's do a real example. Let's do a return matrix that has a universe of 1,000 assets. That's typical, actually. That's kind of like, you know, somewhere between S&P 500 and some high cap, US high cap. Okay, so we have 1,000 assets. And let's give, I don't know, let's go, I'll just make it approximate. But suppose I gave you, here, I will give you one, I don't want to make it square. I'm going to give you, yeah, I'll make it square. Sorry about that. I'm going to give you about 1,000 trading days. That's about 4 years because there's about 250 trading days in a year, so it's 1,000 by 1,000. By the way, this looks you would say, oh my God, that's got 1,000,000 numbers in it. Oh, whoa, you're right. Basically it's the return on any of 1,000 days. That's 4 years of 1,000 different stocks, right? So some column here is Google, and here's Amazon, right? And here is July 12th. Okay, so that's how this works, right? So it looks scary. It's a lot of numbers. 1,000,000 numbers is not a small number. I mean, this is hilariously small. I'm sure you knew I was getting there, right? That I could do this on my phone, but we're going to figure out how long it takes to do this multiplication on my phone, let's say. Okay, and then now I have a portfolio with 1,000 numbers, right? Those are my weights. Who knows where the portfolio came from? It doesn't really matter. Okay, well, the number of flops required is going to be 2mn, and that is 2 times 10 to the 6 flops. Okay, now, by the way, it would take you, if I asked you to multiply this matrix by this vector, it's going to take you a long time because you're going to have to do 2 million floating point operations, right? That's going to take you quite a while, okay, to do. Okay, I mean, that's, of course, the whole point is you don't do that, but whatever. Okay, so it's 2 million flops. And now I'm going to say, how long does it take to do that on my phone? We could do that. We can do my phone, my laptop. Well, let's do my laptop. My laptop can do this with about 10 gigaflops per second. So on my laptop, it would be 2 times 10 to the 6 divided by 10 gigaflops. A gigaflop is 10 to the 9, so this is 10 to the 10. And what you're going to get is, actually, I'll tell you what you're going to get. You're going to get, this is going to be 10 to the minus 4, so it is 2 times 10 to the minus 4, so people would write that as 200 microseconds. Okay, a microsecond is a millionth of a second. Okay, so that says that if you wanted to find the portfolio time series, if someone proposes a weight vector, says, I would like to hold these assets in this thing for 4 years. Please show me my portfolio returns. You're multiplying R times W. And that would take you a shockingly small amount of time. So it would take you 200 microseconds. You could do this 5,000 times in 1 second. That's on my laptop. So I could evaluate 5,000 different portfolios in 1 second on my laptop. Okay, I'm just giving you a rough idea, right, of what it is. But the point is, these are fantastically big calculations being done, and they're done super fast.